Energy and work. What is energy? It turns out that energy is so fundamental, like space and time, that there is no really good answer to this question. Richard Feynman wrote, "There is a fact, or if you wish, a law, governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. The law is called the conservation of energy. It states that there is a certain quantity which we call energy that does not change in the manifold changes which nature undergoes." And this is from the Feynman Lectures on Physics, mainly Mechanics, Radiation, and Heat, from 1963. We may not be able to define energy, but because it is a conserved property of nature, it is a very useful idea. We can do calculations with it, just like with space and time. And with those calculations, we can predict the outcomes of experiments. We can also determine what is possible and what is not possible. Energy is a conserved property of nature. It is not created or destroyed, but it can be moved around. In a closed system that we just talked about, we will always have the same amount of energy. Now, the energy of an open system can change as it's open to the outside. This just means that energy has been added or taken away. But, and here's the key point, the total energy of the system and the environment, which is the universe, always stays the same. If we call the amount of energy that we start with in a closed system E0, and the amount we end up with is EF or E final, then we would say that E0 is equal to EF. This is a statement of the law of the conservation of energy. We can change the energy of an open system by external forces doing work on it. Work can be negative or positive. The equation then becomes initial energy plus work equals final energy. This is called the work-energy equation. Positive work increases the energy of the system, and negative work will decrease the energy of the system. Work can only be done to a system by an external force, a force from something that is not part of the system. If the system is a jet on an aircraft carrier, and the sailors push the jet, they are increasing the energy of the jet. The jet is moving. The sailors are doing positive work on the plane. The amount of positive work done, and therefore the amount of energy increase of the system, is given by work equals FD parallel. So what does that mean? Work is the product of the applied force, F, that moves the object a parallel displacement, and that's what D parallel is. There are some important points to understand about this equation. If the object that is experiencing the force does not move, that means D parallel is equal to 0, then no work is done. The energy of the system is unchanged, a state of equilibrium. Like this acrobat standing on a bunch of support things. Nothing's moving, so there's no work being done anywhere, even though there's various normal forces and gravitational forces. If the object moves in the same direction as the direction of the force, that means the force and displacement are in the same direction, the work is positive. The work is greater than 0. The energy of the system is increased. And we will have an acceleration due to the unbalanced force. Now we've replaced D parallel with delta x, showing that it's a vector along the x-axis or to the right. If the object moves in the direction opposite the direction of the force, that means our force and displacement are in opposite directions, then the work is negative. W is less than 0. The energy of the system is reduced. And once again, we have an acceleration due to the unbalanced force. If the object moves in a direction perpendicular to the direction of the force, in other words, force and displacement are at right angles, then the work is 0. The energy of the system is unchanged. Here's our displacement off to the right. Our normal force is perpendicular, straight up. So is mg, but that's straight down. No acceleration occurs, since no component of force acts in the direction of displacement. No work is done by the normal force or the force of gravity. This equation gives us the units of work. Since force is measured in newtons and displacement is measured in meters, the unit of work is the Newton meter. Since Newton equals kilogram meters per second squared, A Newton meter also equals a kilogram meter squared per second squared. In honor of James Joule, who made critical contributions in developing the idea of energy, the unit of energy is also known as a joule, capital J. Since work changes the energy of a system, the unit of work must be the same as the unit of energy. E initial plus work equals E final. The unit of both work and energy is the joule, and here's James Prescott Joule. Let's work an example. A 60 Newton force is applied to an object that moves 15 meters in the same direction during the time that the force is applied. How much work is done to the object? We have our given. We have 60 newtons in the positive direction and 15 meters, and the force is moving in the same direction as the displacement, so we're going to get a positive work. Here's our work equation. Substitute in the givens, carry out the multiplication, and we get work of 900 joules is done on the object. A 50 Newton force is applied to an object that moves 10 meters in the opposite direction of the force during the time that the force is applied. How much work is done to the object? This time our given is negative 50 newtons. Why negative? Well, since the force is in the opposite direction of the motion, we set the force equal to minus 50 newtons, so our work will be negative. So we have work is force times displacement, negative 50 newtons times 10 meters, and the work done is negative 500 joules. A force does 30,000 joules of work along a positive displacement of 12 meters. Find the applied force. We list our givens. We have the work and we have the displacement. So the work equation, but we need to find force. So we solve the equation for force by dividing both sides by d. Then we input our givens, 30,000 joules over 12 meters, and we get a force of 2,500 newtons. How high can a 40 Newton force move a load when 400 joules of work is done? Our givens are a force of 40 newtons in the same direction as the work, which is 400 joules. So we start with the work equation, rearrange it to solve for d. D is now 400 joules over 40 newtons, or 10 meters.